and welcome to the Chemistry Solution. This video is a general overview of acids and bases and the pH scale. This video is going to cover how we define acids and bases, and we'll take a look at what the pH scale is. In a subsequent tutorial, we will look at how to do some of the calculations involving acids and bases, including how to calculate pH. So I wanted to start by just going over a few of the different definitions of acids and bases. So the Arrhenius definition of an acid is a substance that's going to increase the hydrogen ion concentration when dissolved in water. So that could be something like HCl, which when dissolved in water will ionize to form hydrogen ions and chloride ions. And we know that this method of writing this acid ionization in solution is a little bit of a simplification. We know that in water, your protons are going to interact with water to form hydronium ions. But in these videos, we are going to use the simplification where we use H plus and H3O plus effectively interchangeably, even though we know that the more technically correct way to describe what's going on with these acids is that they are in fact donating a proton to water to give you your hydronium ion. When we look at an Arrhenius base, this is going to be a substance that increases the hydroxide ion concentration when dissolved in water. So this could be something like sodium hydroxide, which will dissociate into sodium ions and hydroxide ions in water, so directly increasing the hydroxide ion concentration. Or it could be something like ammonia, which when dissolved in water will react with water to some small extent to give you the ammonium ion and also some hydroxide ions. When we think about the Brønsted-Lowry definition of acids and bases, this is a slightly more general definition where acids are considered substances that can transfer a proton or donate a proton to another substance, and bases are substances that can accept protons. So you can see something here like ammonia that would be a Brønsted-Lowry base, functions to accept a proton, and also an Arrhenius base because it's a substance that increases the hydroxide ion concentration when dissolved in water. An even more general definition of acids and bases is Lewis acids and bases, where a Lewis acid is going to be a substance that can accept a pair of non-bonding electrons, an electron pair acceptor, and bases are substances that are electron pair donors. Okay, let's talk a little bit about the pH scale. So the pH scale is how we measure the acidity or the basicity of a solution. And when we calculate the pH of a solution, what we're looking at is the opposite of the log of the hydronium ion concentration, or again, because we're using the hydronium ion and our protons interchangeably, we can take the opposite of the log of our hydrogen ion concentration. Where this is a log scale, what it's going to allow us to do is to represent very small hydrogen ion concentrations with numbers that are easier to work with. The other thing the pH scale allows us to do is it allows us to represent a very large range of hydrogen ion concentrations using a scale that, for our purposes, goes from about 0 to 14. So if you think about how log scales work, we're looking at the hydrogen ion concentration with respect to a power of 10. And where we're taking the opposite of the log of our hydrogen ion concentration, what you're going to see is that if your hydrogen ion concentration is 10 to the negative first, all of these concentrations here are in units of molarity or moles per liter. And if we have a hydrogen ion concentration that is 10 to the negative first power, or 0.1 molar, that would give us a pH that's equal to 1. If we had a hydrogen ion concentration that's equal to 10 to the negative second molar, or 0.01 molar, that's going to give us a pH of 2. So a couple of things to notice here. As your hydrogen ion concentration decreases by a factor of 10, your pH increases by 1. So the higher the pH value, the lower the concentration of our hydrogen ion. If you were to look at a solution with a pH of 13, that would mean your hydrogen ion concentration is 1 times 10 to the negative 13th molar, so very, very small. The other thing that I'll point out, and this goes back to this being a log scale and this range of 0 to 14 being able to represent a very wide range of hydrogen ion concentrations, is if you increase your pH by 1 unit, your hydrogen ion concentration decreases by a factor of 10. If you were to increase your pH by another 1 unit, your hydrogen ion concentration is going to decrease by another factor of 10. So in this scenario here, if we were to look at a solution with a pH of 3 as compared to a pH of 1, this solution here with a pH of 3 is going to have a hydrogen ion concentration that's 100 times lower than the hydrogen ion concentration in our solution with a pH of 1. And if we were to continue to increase the pH of our solution to 4, now this solution is going to have a hydrogen ion concentration that's 1,000 times lower than our solution at a pH of 1. So this is a very versatile scale. Okay, let's talk about what these pH units mean in terms of the acidity or basicity of a solution. In a solution of pure water, water can undergo this autoionization process to a very small extent. And what this means is that water can act as both an acid and a base, with one of these water molecules donating a proton to another water molecule, giving you the hydronium ion and the hydroxide ion. If we were to write a simplified version of this reaction, what we would be looking at here is the autoionization of water to give us a hydrogen ion and a hydroxide ion. So again, the simplified version of this reaction here is used very commonly in chemistry, where our hydronium ion and our hydrogen ion are used interchangeably. When we look at this reaction, the extent of this reaction happens to a very, very small extent. And we can represent this mathematically using this constant, which is known as the ion product constant of water. And what this says is that in pure water, this is going to also be temperature dependent. So at 25 degrees Celsius, our hydrogen ion concentration times our hydroxide ion concentration is going to be equal to 1 times 10 to the negative 14th. What this means then is that if we're in a neutral solution, because the stoichiometric coefficients up here are 1 to 1, is that our hydrogen ion concentration would be equal to our hydroxide ion concentration. And if you were to solve for this value here, each of these concentrations would be equal to 10 to the negative 7th molar. Now, in order to find the pH, we know that we can take the opposite of the log of our hydrogen ion concentration. And so if we do that, if we take the opposite of the log of 10 to the negative 7th molar, what we get is that our pH is 7. So if we're in a neutral solution where our hydrogen ion concentration is equal to hydroxide ion concentration, the pH of this solution is going to be equal to 7. We would call that then a neutral solution. But what you'll notice about this constant, Kw, being equal to 1 times 10 to the negative 14th, and being equal to the product of our hydrogen ion concentration and our hydroxide ion concentration, is that if our hydrogen ion concentration goes up, then our hydroxide ion concentration must go down. And so as our hydrogen ion concentration goes up, remember that that means that our pH value is going to go down. And so if we have a solution with a pH of lower than 7, or where our hydrogen ion concentration is greater than our hydroxide ion concentration, then we have a solution that's acidic. Likewise, if our hydrogen ion concentration were to go down, then our hydroxide ion concentration must go up. And if our hydrogen ion concentration goes down, if it gets smaller and smaller and smaller, note that your pH value is going to increase. And so if you have a pH that's greater than 7, or if you have a hydrogen ion concentration that is smaller than your hydroxide ion concentration, we now have a solution that is considered basic. And so the takeaway message from this video is that there are different ways to classify acids and bases, but for most purposes, the acidity of a solution is determined by your hydrogen ion concentration. Generally speaking, everyday solutions are going to have pH values that range anywhere from about 0 to 14. If the pH is equal to 7, that means your hydrogen ion concentration is equal to your hydroxide ion concentration and your solution is neutral. If your pH is lower than 7, that must mean that your hydrogen ion concentration is greater than your hydroxide ion concentration, that your hydrogen ion concentration is greater than 10 to the negative 7th molar, and your solution is acidic. And if you have a solution where your hydrogen ion concentration is lower than your hydroxide ion concentration, this means that your hydrogen ion concentration is less than 10 to the negative 7th molar, then we would identify your solution as being basic. So hopefully that helped to give you a general idea of acids and bases and the pH scale. Check out a subsequent tutorial that will go through some examples of how to calculate the pH or hydrogen ion concentration of a solution using our ion product constant of water, Kw.